For an inclined plane, you still have many of the same forces. For instance, you still have the force of weight, which acts straight down. You still have a normal force, but remember, the normal force acts perpendicular from the surface. When the surface was horizontal, the perpendicular force was just straight up. Well, now the surface is going down at an incline, so the normal force perpendicular from the surface looks like this. And for a block sliding down the incline, what direction do we draw the friction? If the block acts down the incline, then friction must be, that's right, up the incline. So if you have friction, it would look like this. If you had to draw and label a free body diagram, it would look like this. I would look for the weight, I would look for the normal force, and then I would look for friction. If you have friction, it would oppose motion. So for a block going down the incline, or even if it's at rest, it's stopped, it's not moving, it's not going down the incline because of static friction. But anyway, I want to show you where these other forces come from, these components come from. So try to stay with me if you can, and then I'll show you the end result. But when you have the weight acting straight down, it's not in the x and y components of the motion of the object. Okay? So we actually have to find the components of the weight that act into the surface and down the incline. Well, the part that acts into the incline, that force perpendicular, is equal to the normal force. Then you have the force that acts down the incline, right here, that makes the other part of this triangle. Now, this creates a similar triangle to this. I know this seems really complicated. You don't have to be able to remember the method. I'm just showing you where these equations come from here in just a second. The part of the weight that is the adjacent side, we use cosine to find the normal force. The normal force exerted on the block will be the weight cosine theta. The part of the force of weight that acts down the incline, that acts parallel, will be the weight sine theta. So I'm not going to ask you to draw this every time or even ask you where it came from or anything. If you just remember this for inclines, that's what you need to solve. And that's actually what's in your AP prep book. It tells you these equations, but doesn't go into much detail about where it came from. I just wanted to show you that they're actually part of the weight. You don't draw them as extra forces, but like if you're standing on a hill, for instance, part of your weight acts into the surface because you're still standing on the ground, but you can also feel part of your weight almost pulling you down the hill. That's called the parallel force. So this weight that acts straight down, it acts into the incline, and at the same time it acts down the incline. This is the part that acts into the incline. This is the part that's trying to pull you down the hill. That's all that means. And that's what it says up here. For the weight acts straight down, the perpendicular force is perpendicular to the surface, which is why it's like this. If you have friction, it opposes motion. You want to find the components of the weight by finding the parallel force, that's down this way, and the perpendicular force. All right, and so that's all that.
So the one that's into the surface, the perpendicular one, that's the same as the normal force?
Yes, it is. The perpendicular force that acts into the surface will equal the normal force because that's like the reaction force, Newton's third law. However hard the mass pushes on the incline is going to push back on the block. Unless the incline actually breaks or something like that, we can assume those two are going to be the same. All right, so next thing we're going to do is try an example. So I want you to try to draw the free body diagram and solve for these forces, and then we'll meet back in just a couple minutes and try it together.